This guy?
Hey y'all, welcome back. So today we are working on the unit review. So let's get into number one. Let me zoom in here a little bit, make it a little easier to see for you guys. So the strategy here is going to be to create a table defined using the domain. So here we're going from -2 to 2, and plot those points and indicate the direction as well. So here's where our t will go. Over here, I'm going to keep track of my coordinates, my x, y coordinates. And basically, I'm just going to plug in these numbers, -2, -1, 0, 1, and 2, into each individual equation and come up with a table of values here. So when I plug in -2 into the x, I get -2 times 3 is -6 plus 2 is going to be -4. And then if I plug in -2 to the y, I get -1. So I'm going to have a point -4, -1 when t is 2. And then when t is -1, I'm going to, let's see, if I plug that in, I get -3 plus 2 is -1. And then -1 plus 1 is 0. So, hey, look, I got an x-intercept there. How about that? If I plug in 0, I'm going to get 2, 1. If I plug in 1, let's see, just going to standardize my notation here. Okay, so if I plug in 1, I get, looks like 5, 2. And if I plug in 2, it looks like, let's see, 2 times 3 would be 6, plus 2 would be 8, 3. So I'm going to plot these points, kind of keeping track of the order that I plot them in. Let's see here. Let's get a little circle here for the points. And so the first one's going to be at -4, -1, so that's going to be right about here. Then -1, 0. And then, let's see, 2, 1. It looks like this position is moving up and to the right along a linear path. And then we stop at 8, 3. Okay, so I'm going to connect those lines and draw the line. And I also want to indicate the direction. Okay, so basically all you need to do here is draw arrows in between the points you've drawn, showing which direction the motion is. So the position's changing, it's going up and to the right, so I'm going to do little arrows like this. Now, don't put arrows on the outside of these. You don't want to indicate that the graph is going to extend beyond the indicated domain. So you're just going to leave it like that. That's going to be your sketch. I'll just, I know this is number 5, but let's do number 5, and I'll just kind of go down. It'll be easier for me to scroll down than having to keep going down and then come back up. So here, I'm going to construct a very similar table. Using, it looks like, the same t values. And so when I plug these in, if I plug in -2, that'll be 4 plus 5 is 9. That'll be a little off the grid, but shouldn't cause too much of a problem. 9, let's see, -2 divided by 2 would be -1, plus 4 would be 3, so 9, 3. And then if I plug in -1, it'd be 1 plus 5 is 6. And then -1, so it'd be -1 half plus 4 would be like 3.5. 0, if I plug that in, I'll get 5, 4. 0 is usually easy to compute. If I plug in 1, it looks like I'm going to get 6, let's see, 1 half plus 4 would be 4.5, so 4.5. And then finally, if I plug in 2, looks like I get 4 plus 5 is 9, so back to 9, still off the grid, but just barely. And then if I plug this in, 2 divided by 2 is 1 plus 4 is 5. So let's go ahead and start plotting these points and just keep track of the direction that we are moving. So 9, 3, a little bit off of here, so it's going to be like right here. Yeah, and so we got 9, 3, and then 6, 3.5, so it's going to be roughly here. and then 5 comma 4 will be here. Then 6 comma 4.5. So it looks like, yeah, it looks like we're going to have like a nice little sideways parabola here. And then finally 9 comma 5 is going to be up here. So this change in position is going to start by going left and up, and then right and up. So we have a little parabola here, and the arrows should indicate the direction for which it's moving. So try to put some arrows on here. So it's kind of small, so it's kind of hard to squeeze them in there. And you know, if it does get kind of small, don't feel like you need every single one. You just want to get enough to really get the idea down. So this is good enough. So there's number 5. Let's take a number 2, which is going to have a couple of throwback functions here. We've got an absolute value function and a logarithmic function. So we'll construct our table, although this time we're going from 1 to 8. Now, I'm not going to pick every value between 1 and 8 to plot here. They'd be pretty easy to calculate for x. You know, I'm just subtracting 8 minus 1, 7 minus 1, 6 minus 1. But for this log base 2 of t, I want to remind you how to compute this. So log base 2 of t is saying 2 to what power is, and then whatever goes in here. So, for instance, 2 to what power is 2 will be an easy question to answer. 2 to the first power is 2. But 2 to what power is 3 is not as easy of a question to answer. So the values that I'm going to pick here are going to be sort of convenient values. And those particular values are going to be powers of 2 because the base for this logarithm is 2. So I'm going to start at 1. And then, because that would be like 2 to the 0th power. And then 2 to the first power would be 2. 2 squared would be 4, 2 cubed would be 8, and that's probably going to be enough. So if you want to, you know, plug in more values in there, you can, but then you're probably going to have to use a calculator to get those points as precise as possible. And I'm just going to try to run through this without doing a calculator. So for t is 1, 1 minus 1 is 0, and the absolute value of 0 is obviously 0. Log base 2 of 1, so 2 to what power is 1? Well, 2 to the 0th power is 1, so we have a point at the origin. 2 minus 1 is going to be 1, and the absolute value of 1 is 1. Log base 2 of 2, so 2 to what power is 2? Well, 2 to the first power is 2, so log base 2 of 2 is 1. For the next one, we've got 4, so 4 minus 1 is 3. And then log base 2 of 4, so 2 squared is 4. And then finally for 8 here, 8 minus 1 is 7, absolute value of 7, 7. And then, so yeah, the absolute value here really doesn't do anything because all these t values are already positive. And we don't end up with any negative numbers in here. If we did, then we would see something, you know, sort of different happen. But okay, so anyway, so log base 2 of 8 would be 2 to the 3rd power is 8. So we get 3. So we've got our points here. And let's go ahead and plot them out. We're going to start at 0, 0. And then 1, 1. Oh, that's too big. What happened there? And then 3, 2. And then 7, 3. So my graph is going to go up and to the right. It's going to stop there, so I'm not going to extend it beyond that final point. And then my direction is going in this order, so it's going up and to the right. So I'm just going to put some arrows in here to show which direction I'm moving. I don't want to really clutter it in. This is too small, so I'm not going to throw one in there too. But I do want to show like which direction these are moving. So there's number 2. Number 6, similar problem. Actually, all these are going to be basically plotted in the same way. So if the t value here, what's our domain? 0 to 2. So I'm going to do 0, I'm going to do 1, and I'm going to do 2, and that's it for this one. So if I plug in 0, the square root of 0 is 0, and 0 squared is 0, so I get a point of 0, 0. If I plug in 1, the square root of 1 is 1, and 1 cubed is also 1, so That's kind of boring too. And then if I plug in 2, the square root of 2 is going to be like in between 1 and 2. So, if you put that in the calculator, I think it's like 1.14 or something like that. Let's just go ahead and pull it up so we can get a good approximation here. Normally, I would like bypass this and get a different point, one that actually does have a square root. But since our domain ends at 2, I can't really move forward with that. So let's go ahead and see, be a little bit more precise about this. If I can get the calculator to show up, that'd be nice. Okay, there we go. So we get the square root of 2, which is about 1.41. I think I said 1.14. So 1.41, roughly 1.5. I mean, as far as plotting it goes, you don't need to be like precise to the point where you can distinguish 1.4 from 1.5, especially on a grid like this. But anyway, if I plug in 2, the other one, 2 cubed is 8. So I've got 3 coordinates here that I need to plot. I've got 0, 0. So starting at the origin once again, like number 2. And then 1, 1. And then the last point is 1.4, which is really root 2. I really want to stress that it's not technically root 4, it's really the square root of 2. Okay? We're just going to use that 1.4 as an approximation to help us actually plot it out. So 1.4 comma 8 is going to be up here roughly. And then so I'm going to try my best to sketch this out, but this is almost vertical. I mean, look at that. It shoots up really fast, and I'm just going to stop there. So my direction arrows should be pointing this way to show that motion. Number 3, we're starting to deal with sine and cosine. Ooh, we got some secant tangent stuff going on down here. Oh, that'll be interesting. Let's see what's going to happen with that. So for number 3, I've got 2 cosine t and 3 sine t. And we're going between 0 and 2 pi. So I think what I'm going to do here is just pick some values that I can easily find on the unit circle. So for example, I'm going to use 0. I'm going to use 2 pi. It's a good idea to, let's see, can I even, I'm going to have to actually write pi. You know what? I think I have a symbol copied over here somewhere that I might be able to use. There we go. Let's see if this works. Aha. Okay, great. And I'm going to delete these. I don't want to confuse anyone who's just skipping over to this problem. Okay, so I definitely want to go from 0 to 2 pi, but I want to hit some in between. Like, for instance, I want to do pi over 2 should be pretty easy to compute. Pi should be pretty easy to compute, and 3 pi over 2 should be pretty easy to compute as well. Okay, so now let's take a look at this. So we have 2 times cosine of 0. At this point, I'm going to bring up the unit circle so we can see where I'm getting these values from. So at t equals 0, cosine is 1 and sine is 0. So if I multiply the x value, or the 1, by 2, I get 2. And if I multiply the 0 by 3, I still get 0. So I'm going to have 2, 0. There we go. And for pi over 2, which is going to be like straight up, right? We've got 0, 1. So cosine of pi over 2 is 0. Sine of pi over 2 is 1. So if I multiply the x by 2 and the y by 3, I should get 0, 3. At pi, which is directly to the left, I've got a coordinate -1, 0. So the cosine value is -1, the sine value is 0. So if I multiply those by 2 and 3 respectively, I should get -2, 0. At 3 pi over 2, the coordinate is 0, -1. And if I multiply those by 2 and 3, I should get 0, -3. And then when I get to 2 pi, I should have the same value as 0 because those are coterminal. So I should also be at 2 comma 0 here. So let's see what this is going to look like. We're going to plot these points in order. 2 comma 0 is right here. Then I've got 0 comma 3, negative 2 comma 0, 0 comma negative 3, and then back here. So what's happening is I'm getting this, it's not even a circle here. It looks like a little oval. It actually has a name called an ellipse. You don't need to know that necessarily, but it is going to be rotating in a counterclockwise fashion. So I just want to make sure I mark that with those direction arrows. So actually, let's try to just draw it like this. This might work out a little nicer. Yeah. All right, and then I'll put my little direction arrows here to show the rotation that's occurring. All right, so there's number 3. For number 7, similar problem. So I'm going to have the same t values to work with. And let me move this unit circle over so you can see the problem. So if I plug in 0 and I plug in pi over 2 and pi and 3 pi over 2, I'm still looking at those extreme quadrant coordinates. So like 1, 0, 0, 1, and so forth. And I'll take those coordinates and I'll multiply the x by 3 and add 2. And I'll take the y coordinates, multiply the y by 4, and then add 3. So if I plug in 0, I should get 5 comma 3. If I plug in pi over 2, I should get 2 comma 7. If I plug in pi, I'll get negative 1 comma 3. So just, to kind of hit the brakes here, where I'm getting this negative 1 comma 3, is I'm plugging in pi here and here. Oh, you still can't see it. There we go. Move that over just a little bit. You know what? Let me put it up in this corner. So if I plug in pi, for instance, you look at the angle measure pi and report back that coordinate. The x is going to be cosine of that angle, and the y is going to be sine of that angle. So that point is negative 1, 0. So cosine of pi is negative 1 times 3 would be negative 3 plus 2 is negative 1. So that's where the negative 1 is coming from. And then the y, which starts at 0, 0 times 4 is 0 plus 3 is 3. So that's where I'm getting these points from. So like 3 pi over 2, for instance. On the unit circle, you see that's 0, negative 1. So 0 times 3 plus 2 is going to be 2. And negative 1 times 4 would be negative 4 plus 3 would be negative 1. And finally, when I get to 2 pi, I should be back where I started, which is 5 comma 3. Let's go ahead and plot these out. 5 comma 3 is going to be right here. 2 comma 7 is going to be up here. So again, it looks like we're going to be moving in a counterclockwise manner here. Pi is going to be negative 1 comma 3. And 3 pi over 2 will be 2. Looks like I have a negative there. Let's fix that. 2, negative 1. All right, so we'll go ahead and connect the dots here, and then we'll put our direction arrows on there as well. Oh, I lost a point. Was that 2, negative 1? Yeah. So let's try to hit that. 2, negative 1 will be about there. I'll put that point back on there. Okay, there we go. And now time for our direction arrows. All right. Okay, number 4. We've got a combination of a sinusoidal function, and we've got a x equals t 2 to the t. Interesting. I thought I omitted these last two problems, but it appears that they're still there. That's okay. Let's just go ahead and see what we can do here. So we've got a table that has a domain between 0 and 3. I'm going to move my unit circle again because we are going to refer back to that because of the sine function. But anyway, let's do the x's first, okay? And then we'll come back to the y's. So here we want to go between 0 and 3, so 0, 1, 2, and 3. And then, so if like I said, we're going to start with the x's. So 2 to the 0th power is going to be 1. 2 to the 1st power is going to be 2. 2 squared is 4, and 2 cubed is 8. Sine of 0 is going to be 0. I still have that up there? Yes. Sine of 0 is going to be 0, and yeah, that's it. So sine of pi, 1 pi will be 0. Sine of 2 pi is 0. Sine of 3 pi is 0. So we just get 0 down the line. So our coordinates here are going to be 1, 0. 2, 0. 4, 0. And finally 8, 0. So we actually get this horizontal line, or a horizontal line segment. Hey y'all, so it turns out I made a little mistake on this one. And I didn't make any arithmetic errors here. These points all do lie on the curve. But my mistake was assuming that the curve would just sort of follow along these points. In other words, like I just kind of connected these points and didn't really do my due diligence here to look at what was going on in between the points. So I just kind of quickly connected them and called it a day. But upon reflection, I was thinking about these functions, thinking, you know what, like, what are the odds that an exponential sinusoidal function, you combine those, it makes a horizontal, a constant function? That just, like, didn't seem right. So what I went back and did was I looked at some values in between 0, 1, 2, and 3, so like 0.5, 1.5, 2.5, and saw that, sure enough, this function is not going to be horizontal. Now you can plug in, like if you plug in a half, and you can evaluate each one of these, but just to kind of save some time here, I'm going to let the calculator do the computations for me. And so as you can see, I've typed in an equation for x and an equation for y. And if you're curious how I got to this parametric mode, I just hit mode and changed it from function to parametric. So going back to y equals, I've got this xy setup. And now if I hit second table, the default here just has 0, 1, 2, 3, just the integers here for t values. And you can see that all my values here are correct, right? Like 1, 0, 2, 0, 4, 0, all those points are correct. But if I change this to go, instead of just giving me every integer, to get those halves, like 1 half, 3 halves, 5 halves, we get points that are not along that line. So what I need to do here is I'm going to erase my segment. I'm going to keep these points where they are because they should be there. But what I'm going to do now is I'm going to plot these points in between so you can get a better idea of what's really happening here. So if t is 1 half, I have a point here at about 1.4, 1. So that's going to be about here, roughly. And then at 1.5, when t is 1.5, I've got a coordinate at about 2.8, negative 1. So 2.8 negative 1 is going to be here. Trying to make this little dot here. And then my next point, I've got the 4, 0. When t is 2.5, I've got about 5.6, 5.7, 1. So that's going to be here. So now I think I'm safe to finally connect these points. Let's go ahead and do that. Starting at 1, 0,
the curve is going to go up and come back down. And basically what we're going to have is this kind of like a sinusoidal function that's being stretched out, but not in a linear way where each peak is going to be like equidistant from the next peak. They're going to be spaced out in an exponential way, where like the first wave is going to be sort of skinnier than the next one, which will be skinnier than the next one. Every single iteration of this cycle is going to be more spaced out than the last. So the last thing to do here is to throw on these little arrows, these direction arrows, to show the direction going from left to right here. And there you go. So this is really what number 4 should look like. Let's go ahead and go back to the video.
All right, so for number it says find a set of parametric equations using this defined parameter. So what this parameter is going to do is it's going to give us the x equation for each one of these in terms of t. So what we need to do is we need to rewrite this particular equation. I'm just going to retype it up here so you can see how I'm going to rearrange it. I'm going to start by subtracting 2 from both sides. And then I'm going to divide both sides by 3. So what I'm going to end up with is 1/3 t minus 2/3 equals x. And so this is going to be my x equation for each one of these sets of parametric equations. And then to get the y, so let me just go ahead and copy and paste this for all 3 of them. To get the y, we're going to take this expression and substitute it into x right here and simplify. So I've got y equals 4 times all of that minus 1. And then to simplify this, I would distribute the 4. So 4 times 1/3 would be 4/3. And 2/3 times 4 would be 8/3. And then minus 1. So 1 as a fraction would be 3/3. So this will end up being 11/3. So there's your set of parametric equations for A. For B, we're just going to substitute this into x, and we can actually just leave it like that. We don't need to cube out the entire thing. So I'm just going to say that y equals that x cubed, and it's safe to leave it there. We could have probably done that over here too, but there's really no reason to cube this out. C, we're going to substitute this in for x, and then it looks like we need to square both sides after that, because this one, notice it's solved for x in terms of y rather than the other way around. So we'll get, that's my x equals the square root of y. And then so to isolate that y, we're going to square both sides. So I'm going to square this entire side, and that should equal y. Again, I'm just going to leave it like that. You could square this out by using FOIL or just really using the distributive property, but I'm going to leave it like that. But anyway, we're going to write a set of parametric equations to represent this line. Now I want you to notice something about this line. It's got a y-intercept of 5. It is linear, and it looks like the slope is just 1, up 1 over 1 the whole way. So the rectangular equation here is going to be y equals 1x, 1 being the slope, minus 5, because 5 is the y-intercept. We do not need to put this 1 there, so I'm just going to leave it as x minus 5. And then for the domain of this rectangular equation, we can see that the minimum x value is 0, and the maximum x value is 7. So we'll say that x is in between, not 1, but 0 and 7. We don't see open circles here, so we'll just assume that we do include the endpoints. So this is the rectangular version of the equation, and we will use this parameter to rewrite it. So this is a parameter is given in terms of y, which is kind of interesting. That's not very typical, but we could still solve this for y, and then we'll plug it in and simplify and so forth. So interesting here. Let's see. So we get, we're going to add 2 to both sides. So we get t plus 2 equals 2y. And then divide everything by 2. So I get 1/2 t. Oops. 1/2 t plus 1 is y. So here's my y equation. And then I can substitute this in for y to get an x equation. So that's what I'm going to do next. So there's my y, and then equals x minus 5. And if I'm solving this for x, I'm just going to add 5 to both sides. So that'll leave me with x equals 1/2 t plus 6. The last thing we're going to do is try to rewrite the domain here in terms of t. So if we start with x being in between 0 and 7, and that we know x is 1/2 t plus 6, it can replace the x with 1/2 t plus 6. So to simplify this, or to solve it for t, we're going to first subtract 6 from both sides. So this will be negative 6, 6 minus 6 is 0, so this will go away, and 7 minus 6 is 1. And then we need to multiply both sides by 2. So negative 6 times 2 would be negative 12. 1/2 times 2 is 1, which is what we want to happen. And then 1 times 2 would be 2. So this is going to be the domain in terms of t. And here is my set of parametric equations. So usually you write the x first. So I'm just going to rearrange these a little bit. There you go. Okay, so that's the answer to that one. It says eliminate the parameter to express y as a function of x. So pretty simple here. What we need to first do is rewrite this in terms of t, or rewrite this so that we have t isolated in terms of x rather. So if x is 4 minus 2t, we're going to start by subtracting 4 on either side. So minus 4, 4 minus 4 is 0. And then divide both sides by negative 2. So we have negative 1/2 x, and then negative 4 divided by negative 2 would be positive 2. So here's what t equals in terms of x. So we're going to substitute this into t for the y equation. So y, so like this whole thing right here, we're going to put right here. So y equals the square root, if I can find that square root button, there we go, 2 times negative 1/2 x plus 2 minus 3. So if I distribute this 2, two times negative 1/2 will just be negative 1. And so you don't really need the 1 here, but I'll just leave it there temporarily. And then 2 times 2 is 4, and 4 minus 3 is 1. So we get the square root of negative x plus 1. And we want the domain of this function. Now the original domain is in terms of t. And since we're taking the square root of this, the only domain restriction here would be that t, or not t, but what's underneath the square root has got to be at least 0. Because if it's negative, then we're going to end up with non-real values for y. So we're going to say that 2t minus 3 has got to be greater than or equal to 0. So if I solve this for t and add 3 to both sides, and then divide both sides by 2, I get t is greater than or equal to 3/2. So if I'm trying to find the domain in terms of x, I'm going to substitute t for what t equals in terms of x, which is this negative 1/2 x plus 2. And solve for x. So I'm going to subtract 2 from both sides. This right here is 1.5. So 1.5 minus 2 is going to be negative 0.5. And then I'll multiply both sides by negative 2. And so I should get x is less than or equal to 1. I've got to flip the sign anytime I divide or multiply both sides of an inequality by a negative. So this would be the domain, and we didn't really need to find it like in terms of t first. We could have just found the domain from here. Like if I just said that a negative x plus 1 has got to be greater than or equal to 0, because that's got to be positive or 0. It's going to be non-negative. And subtract 1 from either side here. So we get negative x is greater than or equal to negative 1. And then when we divide both sides by negative 1, we end up with this same statement. So you can arrive at this domain either way. You just have to know what the domain of a square root function is to really start it. So that's why this is kind of a bonus. Just hey, in case you happen to know that, you might get a little extra credit there. So there's the domain of the function. Here's the actual answer to the question, which is to express y as a function of x. Right. So there's our equation right there. A little bit of a throwback to vectors here, but really you don't need to know anything about vectors except just really understand this notation and know that the first number is our x, the second one is our y. So in this case, I'm just going to rewrite the function as a set of parametric equations here just to make it look more like what we've been doing in this unit. So x is equal to 3t squared plus 14t, and y is equal to sine of pi t. And the question is, when does this pass through the point negative 8 comma negative root 3 over 2? So we need to solve one of these equations and then use our t to check, use our solutions and check the other one. So I'm going to start by substituting negative 8 into x here, and we'll solve that one first. So if x is negative 8, we want to know when does that happen? At what time is the x negative 8? So this is going to be a quadratic. We need to set it equal to 0, so we're going to add 8 to both sides. And at this point, I'm going to try to factor. I'm crossing my fingers. Hopefully it's factorable. If not, it's not the end of the world. We can use quadratic formula. But let's see if we can't factor this. So to factor it, we're going to first bring down the first and the last terms. And we will try to figure out how do we split up that middle term. Well, we need two values whose sum is 14. And this process is called factoring by grouping, by the way. I know we've done it a few times in this unit, so I don't want to rehash it too much, but that is what it's called. So two numbers that add up to 14, this middle term, and those same two numbers need to multiply to give you the product of the leading coefficient and the constant. So 3 times 8 is 24. When you try to think about this, I think the easiest way to approach it is to start with the factors, meaning like the two numbers that do the multiplication, because there's going to be a lot fewer combinations that you have to think about in terms of finding two numbers that multiply to give you 24 versus finding two numbers that add up to 14 if you're just working with positive integers here. So like you could do 1 and 24, 2 and 12, 8 and 3, 6 and 4, and that's about it. And the only combination here that's going to also add up to 14 would be 12 and 2. Right, 12 times 2 is 24. 12 plus 2 is 14. So those are going to be the two middle terms that this 14t will break up into. 12t plus 2t. All right, I just kind of want to show where all these terms are coming from and going to. At this point, we're going to group. So we're going to group the first two terms and the last two terms and come up with the GCF out of each group. So the first GCF would be 3t, which would leave us with t plus 4. And the second GCF would be 2, which would also leave us with t plus 4. And that's what tells us that we're likely doing it correctly here when we get the same thing in parentheses on both sides. So the two factors here are going to be t plus 4 and 3t plus 2. And so the two t values, looks like there's going to be 2 times when the x value is -8. The first one would be at -4, and then the second one would be at -2/3. And I'm getting those from just setting each factor equal to 0 and solving them. So this is not going to be our final answer here, but these are going to be two values that we can test in this sign equation and see, hey, which one is giving you -√3/2. So we're going to plug these in, both of these into this equation, and we're going to test and see which ones work. So first we'll plug in -4. So sine of essentially -4 pi. We're going to evaluate that. And then we're also going to evaluate sine of -2 pi over 3. And it could be that both of these work. It could be one of them works. It could be none of them work. So whichever ones end up equaling -√3/2 are going to tell us which times are correct that satisfy both of these conditions. So I'm going to bring up my unit circle, get it out of the way here. And so the sine of -4 pi, so as you look at your unit circle, you're going to spin around essentially twice, right? One full revolution is 2 pi radians. And if I go the negative direction, meaning clockwise, I'll spin around twice and end up back at 0. And so the sine of that angle measure would be 0. So that is not what we're looking for. We want it to be -√3/2, so we can conclude that time equals -4. Unfortunately, that is not going to satisfy the second condition. At time equals -4, the x is -8, but the y is not -√3/2. Now, if I look at -2 pi over 3, which is coterminal to 4 pi over 3, so it should have the same y value, we do get -√3/2. So -2/3 is going to be the only time that satisfies both of these conditions. So let's go ahead and write -√3/2 here. Don't really need the unit circle for now. So yeah, so this one, the first one did not check out. The second one did check out. So our answer is just going to be t equals, oops, -2/3. And only -2/3. So we do not want to include that -4 in our solution set. So that's the end of page 2. Let's take a look at page 3. We've got, again, our parametric equations, which are kind of written like vectors, but if we want to write them a little bit more traditionally like parametric equations, I can rewrite it like this, where x is t squared plus t minus 12, and y is 2t minus 1. We want to know, when is it in quadrant 2? So quadrant 2 is the top left quadrant, and in quadrant 2, here's 1, here's 2, here's 3, here's 4, and yes, this is supposed to be a 2. There we go, let's make it a little bit more 2-ish. And in quadrant 2, the x is negative and the y is positive. So what we need to do is set up, oh gosh, my handwriting stinks with this mouse. The y is positive. So what we need to do is we're going to set the x to be less than 0 and the y to be greater than 0. We'll solve both inequalities and then try to identify where the overlap occurs, meaning that we need to find t values which satisfy both equations. Okay, so we want to know, when is x negative and when is y positive? So let's do the easier one first. This 2t minus 1, we're going to add 1 to both sides and divide both sides by 2. So we get t is greater than, well, here, I'll just show the steps here. So 2t would be greater than 1, and then dividing both sides by 2, I would get t is greater than 1/2. Over here, for anything that's not linear here, I would just say throw it in the calculator and then look at the graph and find, like in this case, when is it less than 0? Or for what t values is the graph below the x-axis? So let's turn on the calculator. I'm going to go to y equals and type in my equation here. So move the calculator out of the way so you can kind of follow me here. T squared, so really just x squared plus t minus 12. And I'm looking at the graph trying to figure out when is it going to be negative or when is it going to be below the x-axis. And so you can see it's below the x-axis, like down here. And so the t values are going to be in between, what is that, 1, 2, 3, -4 and +3. So we'll say t is in between -4 and +3. In a future unit, we will go into much more detail on how to solve something like that algebraically, but for now it's fine to just use your calculator. So, all right, we want to find which t values satisfy both of these inequalities, because it's got the x has got to be negative and the y has got to be positive. So what I'm going to do to help us visualize where the solution set is going to be is I'm going to draw a number line here and just express, okay, where are these solutions? So t greater than 1/2. So let's say 1/2 is here. This would be like an open circle pointing to the right. Yeah? So all these would satisfy the fact that y is positive. And then where x is negative is in between -4 and 3. So this statement says, okay, well, t's got to be between -4 and 3. So in other words, all the numbers in between here and here. So which t values will satisfy both conditions? And that's going to be these values in here, okay, the overlap, essentially. And so our final answer here is going to be that t needs to be in between 1/2 and 3. So any number between 1/2 and 3 will work for this inequality and this inequality. All right, last problem here. Find the distance from f to g when t is 3. Okay, so let's first figure out, like, where are these objects when t is 3? Okay, so what we need to do is plug in 3 into t and say, okay, well, where's f and where's g? So I'm going to say, like, f is at some point when t is 3, and g is at some point when t is 3. So to figure out where they are, we're just going to plug in t and simplify. So for f, we have cosine of 3 pi, which, if I look at my unit circle, 3 pi would be coterminal to 1 pi, and the cosine is -1. So f would be at -1, comma, and then for the y coordinate, we have the square root of 1/3 t. So 1/3 times 3 would be 1, and the square root of 1 is 1. And then for g, we'll do the same thing. We're going to plug in 3. Okay, right here, 4 minus 3 is 1. And the natural log of 1 is 0, and 0 plus 4 is just 4. For the y coordinate, we've got the absolute value of -t minus 2. So first of all, -3 minus 2 would be -5, and the absolute value of that would be +5. So this is going to be like where they are. You know, the x and the y coordinates are given. So now we just need to find the distance. Okay, so we're just going to use this. You can either think of it as the distance formula or think of it as the Pythagorean theorem. I'll just give you a quick little visual and showing you what it is exactly we're trying to find. So negative 1, 1 would be like, negative 1, 1 would be roughly right here. And then 4 comma 5, 1, 2, 3, 4. So 4 comma 1, 2, 3, 4, 5 would be roughly right here. So this is just like at this particular time, that's when where these two objects are. So to find the distance here, like the distance from this point to this point, you can use distance formula if you know it, or just set up a little right triangle and use Pythagorean theorem. Okay, you can see that the distance of this side is 4 and 1 is going to be 5. This one would be 1, 2, 3, 4, 4. And so we would do the distance that's weird. I don't know why it's writing it like that. Actually, I think I might know why it's writing it like that, but the distance is going to be equal to the square root of a squared plus b squared. So in this case, that'd be 4 squared plus 5 squared. And then we will simplify that. So 4 squared would be 16. So 16 plus 25 would be, looks like 41. And so that would be the distance.
We've got one last problem here. It says the path of two objects are described by the parametric equations below, and they give you the two sets of parametric equations for each object. And it's asking whether or not the paths intersect. If so, where? So we'll find out whether or not the paths of these two objects intersect. And then a little bit lower, it's going to ask whether or not they collide. So we'll get to that in a minute. But first, let's find out whether or not their paths intersect. And to do that, we are going to try to convert each set of parametric equations into a single rectangular equation and solve that set of rectangular equations as a system of equations. So first, notice how we've got x equals t. So we can substitute x, since that equals t, we can substitute that into t for the other equation. And I'm going to kind of solve both of these at the same time, just so that you can kind of see that you do the same steps for any of these. For object 2, x is going to equal all this. Now what I really want is to be able to substitute something in for t in the second equation. So I need to rewrite this equation where it is where t is isolated. So I'm just going to retype this as x equals 2t plus 1. So just retyping that. And then if I subtract 1 from both sides, that's going to give me x minus 1 equals 2t. And then if I divide everything by 2, I'm going to get 1/2 x minus 1/2. So that's t, and I can substitute that into t for the other equation. So basically right there. Okay, so I'm going to end up with two equations here. For object 1, these two, I'm going to end up with this equation that I'm going to type over here. And then for object 2, I'm going to type that equation right here. And they're both going to be linear equations. They're both going to be solved for y. So the first one is going to be y equals, and then instead of t, I'm going to write x, since t equals x. And since it's just a single term, or a single variable there, we don't really need the parentheses. It's x squared plus 2. And then for this one, I'm going to write this, I'm going to essentially rewrite the second equation, except instead of t right here, I'm going to write 1/2 x minus 1/2. So y equals 1/2 x minus 1/2. And I do have that plus 4 kind of hanging on the end, but just to make that a little simpler, I'm going to combine these two constants. So 4 minus 1/2 would be 3.5. This would be like 8/2, so 8 minus 1 would be 7/2. So plus 7/2. So now I've got two equations. They're both, actually this one's not a linear equation, this one's a quadratic, but they're both in two variables and both solved for y. So we can solve this as a system of equations by setting the two y's equal to each other. Since y is just y, we can essentially set these two expressions, this x squared plus 2 and the 1/2 x plus 7/2, set them equal to each other and solve for x. So let's go ahead and type that out. We've got x squared plus 2 equals 1/2 x plus 7/2. And we need to solve this. So one thing I'm noticing here is I kind of want to get rid of the fractions. That's kind of annoying me right now. So I'm going to multiply everything by 2 just to clear those fractions out, and I think it'll just make the solving process go a little easier. So I've got 2 times x squared would be 2x squared, 2 times 2 would be 4, 2 times 1/2 is 1, and 7/2 times 2 would be 7. So just kind of clean up those fractions a little bit. Now anytime you're solving a quadratic, you need to set it equal to 0. So I'm going to move this x plus 7 over to the other side by subtracting both x and 7 from both sides. So that's going to give me 2x squared minus x, and then I have that plus 4 minus 7 equals 0. So I can combine the 4 minus 7, and that would give me -3. So now I've got quadratic, and I've got a couple of options here. I could try to factor it, which is usually my go-to option, or I could use quadratic formula. If you know the quadratic formula, that could also work for you. But it looks like we may be getting 2 points of intersection, which would make sense because this first object is going to have like a parabolic path, and the second object is going to be a line. So if you imagine a parabola and a line, it kind of makes sense that they would cross twice. So let's see if we can factor this. The two first terms have got to multiply to give me 2x squared. So really my only options here are 2x and x to get the 2x squared. And then I need two numbers that multiply to give me -3. So not a whole lot of options here, just 1 and -3 or -3 and 1. So I'm just going to throw something out there and see if it works. I'm going to do -3 and plus 1. So to check to see if it works, we need to multiply 2x by 1 and then -3 by x. And if those add up to -x, then we're good. So this would be 2x minus 3x is -1x. So these are my two factors. So once I get the two factors, I'm going to set each one equal to 0 and solve them individually. So either 2x minus 3 is going to equal 0 or x plus 1 is going to equal 0. So solving this, the left one, I'm going to add 3 and divide by 2, which will give me x equals 3/2. And then over here, I get x equals -1. So these represent two x values where the two paths are intersecting. Now, we haven't decided whether or not they're happening at the same time, but we'll answer that in the next part. So these are the x coordinates. We don't have the y coordinates yet, so we need to get those separately. So let's see here. So it doesn't really matter which one we're going to plug this into. We could plug it into this one or this one, whichever one seems like it's going to be easier to simplify. Kind of leaning more towards the first one. Yeah, I think that's the way I'm going to go here. So to get the y for x equals 3/2, okay, so I'm going to box this, but this just, remember, these are not really my answers. I just want to kind of make them stand out a little bit. Let's see here. So we've got y equals x squared plus 2, so that would be 3/2 squared plus 2. And then for the other one, for where an x is -1, we've got y equals -1 squared plus 2. So 3 squared would be, 3 squared is 9 and 2 squared is 4 plus 2. And over here, -1 squared would just be 1. So I've got, let's move these up just to, oh gosh, what happened there? Okay. Let's try that again. Okay, really I just wanted to move these up to kind of give me just a hair more room, just a little bit. There we go. Okay, so
9/4 plus 2. Now 2 would be 8/4. So 8 plus 9 would be 17/4, which I don't think, yeah, that cannot be reduced. And then over here we've got y equals 3. So we've got two coordinates where these objects' paths are going to intersect. So the paths intersect? Yeah, they do. We just found where, yes, at, well, I think I'm going to have to write this using, I'm going to have to type this out using the equation because I've got these fractions. So at 3/2, comma, 17/4, and so that's one location. And the second one is going to be at -1, comma 3. So we do have 2 points of intersection for these two paths, but the second part of this question is all about the collision. So let me just kind of wrap this up, box my answer here. So the second part of this says, do the objects collide? And in order for them to collide, they have to be at the same place at the same time. So what we need to do is we need to substitute these coordinates back into the object equations and see whether or not we get the same time. So let's plug in x. So let's start with the first one. So I'm just going to kind of look at these separately. So we have a potential collision here, and we have a potential collision at -1, 3. And so we need to see what time each object was at that location. So I think what I need to do here is I'm just going to take a second to retype these parametric equations. So x plus t and y equals t squared plus 2. That's the first one. So we'll see, okay, where's object 1? Or rather, when is object 1 at this point? And then we also need to know when is object 1 at this point. And then we need the equations for object 2. So I'll go ahead and type those out so I can not have to keep scrolling up and down here. Okay. All right, now just to keep this a little straightened out, I'm just going to throw some lines here just to kind of divvy up what I'm doing. Okay, so yeah, so we've got the first point of intersection is at 3/2, comma 17/4. So I'm going to plug this into x, the 3/2, and this into y, and just see at what time they actually are there. So let's plug it into the first one. Okay, so if x is t, so 3/2 equals t, right? So hopefully the other one is there as well. We could also plug it in here, 3/2 plus 2. So let's see. So, I'm sorry, the y is 17/4 equals t squared plus 2. So if I subtract 2 from both sides, I'm going to get 17 minus 8, which would be 9/4, equals t squared. We're not really expecting this to be different, but it's good to just double check. Take the square root of both sides, you get t equals 3/2. So yeah, we do get 3/2 as the time at which the first object is at this point. And so this one just needs to match it. So we'll see. So the first one says x, which we said is 3/2, is equal to 2t plus 1. So we're going to subtract 1 from both sides. It's going to give me 1/2 equals 2t. And then divide both sides by, looks like this is not going to be a collision. Okay, because if I divide by 2, I get 1/4. Okay, this is a different time. So that means the x-coordinate of that second object is not going to be in the right place at the right time. So
no collision here. Okay, so we can go ahead and just stop here because we do need the same time for this point. So no collision. Now that's just at this coordinate. We're gonna test the other one as well. So for this other one, we've got x equals, okay, so x equals t. Okay, so -1 is t. And then the y should be 3 here. So 3 equals t squared plus 2. I'm going to subtract 2 from both sides. So that's going to give me 1 equals t squared. And then if I take the square root of both sides, I do get plus or minus 1. Now, obviously, plus 1 is not going to be one of our answers here because we're looking for the x value to be, or we're looking for the time to be -1. So that will match. So we get t equals plus or minus 1, but we want to discard the positive 1 because as we see from this first one, we want the time to be -1. Okay, so now we see that we got the same time here for the first object. So that checks out. Time is -1 for that first object. Let's check the second object. It's going to be kind of disappointing if we don't have a collision, but you know, sometimes that's just how it works out. So for the second one, I get x, which is -1, equals 2t plus 1. I can subtract 1 from both sides. So that's going to give me -2 equals 2t. And then divide both sides by 2. So that's going to give me -1 equals t. Okay, so far we are on the right track here. We get the same time. It's looking like we potentially have a collision at -1,3 at t equals -1. So let's check the second, the y coordinate here. The y coordinate is going to be 3. So 3 equals t plus 4. If I subtract 4 from both sides, I do get -1 for t. So yeah, so we do have a collision, not at this first intersection, but at the second one. So the way we want to word this, we say, yes, the objects collide at -1,3 when t is -1. And that's going to be our answer for this last question. So that's it. That's the end of the review. Let me know if you guys have any questions, and other than that, y'all have a great day.